Hello students, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in the last session of lecture number 7, so where we discussed about the angular momentum introduction, right? So angular momentum in the circular motion and what is the angular momentum formula. So how do we solve the questions related to it? So all these things we covered in the last session. So we are going to continue with the same concept. So that is in today's lecture. So what's our topic, main agenda? So the angular momentum of a purely rotating body first, then the Newton's second law for the rotational motion, and then so the conservation of angular momentum. So these questions, the questions based on these concepts are very important. Okay, and then questions on conservation of angular momentum. Okay, clear? So these are our main objectives today. So as usual, I just need your attention for the next 1 hour, guys. Just be with me, avoid all the disturbances around you, and at the end of the lecture it's a very important to prepare your own short notes. Okay, chalo. So with very high positive energy, let's start the today's topic. So what's the first topic? The angular momentum of a purely rotating body. So for a circular motion, so for circular motion, the angular momentum formula we have already discussed in the last session for the circular motion, right? So what is that? L is equals to simply mvr. This we already discussed. Now for purely rotating body, for a purely rotating body, so shall I write, I am going to use the same formula. From here I'll modify that. So L is equals to actually mvr. So if the body is rotating, so then so in the rotational motion we know that v is equals to r omega. Yes. So now L is equals to m into, in place of v I am writing r omega. See, same concept. How we got mvr? mvr sine 90 degrees. The angle between r and v is 90 degrees, right? So I am not writing that here. So in place of v I am writing r omega into r. So now L is equals to m, so r into r square into so omega, right? So from here the L is equals to, so I can write I omega. So what is this? Moment of inertia, right? This mr square is nothing but the moment of inertia, so into omega simply. So right, this is a formula for the angular momentum of a purely rotating body, which is L is equals to I omega. Sir, can we write it in the vector form? Yes, angular momentum is a vector quantity, guys. So you can write it in the vector form. So how do we write it in the vector form? Simple thing. So L is equals to I omega. So one important thing, that is, so whatever the axis about you are taking the moment of inertia, so or else whatever about the axis you are taking the angular momentum, so the same moment of inertia you have to take. So about the same axis you have to take the moment of inertia. So L about which axis you are finding, so the moment of inertia also you have to take about the respective axis. So let's suppose if you are finding the angular momentum about the a line which is perpendicular and passing through the center of the uniform rod, so then you have to take the moment of inertia also for the same. Okay, so into the omega. So this point you should remember, guys. Clear the concept? Chalo. So this is a first important note for today's class. Chalo. So let's move further. Hope my voice is clear, everyone. So now we know that for the translationally motion, L is equals to r cross p, right? We already studied this. And then L is equals to, we can write that r into, in place of momentum, so mv. So v is a vector quantity. Now L is equals to, we can also write that, so mv r perpendicular r, you can also write it as L is equals to m into v perpendicular into r. You can also write it as L is equals to m into v perpendicular into r. So that's also fine, right? So now for the rotatory motion, just now we derived, so L is equals to I omega, guys. So L about which axis you are finding, so the moment of inertia also you should take about the same axis. into omega, okay. So analogy, with the analogy also you can remember this. So the simple way to remember this, is, so just do the analogy of linear motion versus rotational motion. So analogy of, so let me do, so in the linear motion, in the linear momentum, so we know that P is equals to mv. So the momentum P is equals to mass into velocity v. Now, so in the angular term, how can we write? So in the angular term, so I can write the same thing as, so P, in place of P, what is the equivalent of P in angular? So which is nothing but, so the angular momentum L, linear momentum and angular momentum. So in place of mass, we can write moment of inertia. In place of velocity, we can write omega. Yes, so this is a formula. Clear? I omega. So the simple way to remember, just compare. Done? Clear? Chalo. So let's move further. So let's take one simple question, guys. So what's the question says? What's the question says here? Find angular momentum of a, so this is of a, find angular momentum of a solid cylinder of mass m and length L and radius r when it is rotated about its center of mass as shown. So about its center of mass as shown, this axis, about this axis it is rotating. So we have to find the moment of inertia. See, so not moment of inertia, we have to find the angular momentum. So the angular momentum is equals to, so we now know that L is equals to I omega. Moment of inertia is a scalar quantity, guys. Okay, so here I can write L about which axis you are finding. So the moment of inertia, you have to take that, you have to take about that particular axis, respective axis, into, so omega, into omega. Chalo. So the moment of L about axis, so some axis they said, so which is equals to, for the solid cylinder, this is a solid cylinder, the moment of inertia about this axis we already know. For the solid cylinder, if it is about, see, if it is about this axis, it's going to be mr square, mr square, disk, same as of the disk, mr square by 2, mr square by 2. So but they are asking about this axis, so we already discussed it in the class. So what is that? Mr square by 4 plus mr square by 4 plus ml square by 12, mr square by 4 plus ml square by 12. So this is a moment of inertia of this into the omega. So that's it. This is a total angular momentum about the respective axis. So this is a total moment of angular momentum about the given axis. Clear? Just you have to aware of the what is moment of inertia. Clear? Chalo. Chalo. So let's take the next question, guys. What's our second question says? A uniform rod of mass m and length L is rotated about an axis passing through the point O as shown in the figure. See here, this point is, this is the axis. It's not passing through the center of mass and it is not passing through the end, right? So consider this is a center of mass. So we know about the center of mass actually. So about center of mass, we know that it's equals to ml square by 12. So but here we don't know about this particular axis. We can apply the parallel axis theorem. So they are asking what is the, find the angular momentum of the, find angular momentum of the rod about the rotational axis. See, so L about that particular axis will be equals to moment of inertia about that axis plus, into omega. So here L about that axis will be equals to, so I can write, so the first thing is the moment of inertia about the respective axis I have to find. The moment of inertia about the respective axis I have to find. So how do we find? We know about the center, and then this distance will be L by 4, because this is L by 4, this will be L by 4, right? So the moment of inertia according to the parallel axis theorem, ml square by 12 about its center of mass plus, and then so the other one which is at a distance L by 4. So m into, so what's the distance? L by 4 whole square, right? So this is a formula. So this is a formula. So from here, so ml square by 12 plus ml square by 16. So here what will be the LCM? So 48, and then we get, so this is 4 times 4 ml square plus this will be 3 ml square, right? So total 7 ml square by 48. So this is a moment of inertia. So now what is angular momentum? L about the given axis is equals to moment of inertia about that axis is 7 ml square by 48 into, so omega, in place of omega, right, omega naught, because in the question they gave it as omega naught. Okay, so you can simply take this as the answer. Understood? Clear everyone? Done this part? Chal. So fine. So what's the option? Is option is there? Yes. So option 3 is the correct one. See, some students might be thinking that, sir, why we have to apply the parallel axis theorem only here, like ml square by 12 plus m into L by 4 whole square. So we can apply the parallel axis theorem here also. I know about this axis, which is ml square by 3 about one end, plus from end it is at a distance of L by 4, and those two axes are parallel. We can apply the parallel axis theorem there also. No, because parallel axis theorem can only be applied if one of the axis is passing through the center of mass. Okay, so one of the axis should pass through the center of mass, then only you can apply the parallel axis theorem, otherwise no. Okay na? Clear? Chal. So this question is fine. So now let's go for the next. So the angular momentum and kinetic energy. So the angular momentum and kinetic energy. See, the simple thing is, we know the angular momentum L is equals to mvr. The angular momentum L is equals to mvr. And then, so what's the kinetic energy? L is equals to, the kinetic energy, better, let's take this formula. So L is equals to I omega, we know. This is the angular momentum in terms of moment of inertia and omega I am taking. And then kinetic energy formula also, you know. Which kinetic energy we are talking about here? The rotational kinetic energy, the rotational kinetic energy. So half into, so I omega square, half into I omega square. So now what I am doing is, so let's write here. So here let me take, so the kinetic energy, the rotational kinetic energy is half I omega square. Now, so from this equation, let me write omega is equals to L by I. Omega is equals to L by I. Let's substitute this here. Okay. So then the kinetic energy will be equals to half into I into, in place of omega, let's write L by I whole square. In place of omega, I am writing L by I whole square. So then the kinetic energy is equals to half into I into, so here L square by I square. Simple calculations. I gets cancelled, so that we get kinetic energy K. Let's write kinetic energy as K. So K is equals to half into L square by I. So from here, let me write I is equals to, or else L square is equals to 2ik. L square is equals to 2ik. From here, the L is equals to root over 2ik. Yes or no? So the L is equals to root over 2ik. See here. So what we are doing here, actually we are establishing a relation between the angular momentum and rotational kinetic energy. So L is a angular momentum here. L is a angular momentum. Okay. And then, so K is a rotational kinetic energy here. In this particular case, K is a rotational kinetic energy. Okay na? Understood? So to remember this formula, you can simply follow the analogy. So let me write it in the next slide. So you can simply follow the analogy, guys. So what's the analogy? So let me check, do we have this template? So no, let's go with the normal one. So see here, the analogy. So in the case of linear motion, so we know that the relation between linear momentum and kinetic energy, we already established this that relation, P is equals to root over 2 mk r. So the kinetic energy K is equals to P square by 2m. The kinetic energy K is equals to P square by 2m. So this is the in linear motion. So now come to the angular terms, come to the angular rotational part. So in this case, so just in place of momentum, so what you can write, in place of linear momentum you can write the angular momentum L, which is equals to root over 2 into, so what is the mass equivalent in angular? Mass equivalent in angular is, so the moment of inertia I. So into, so what's the kinetic energy? K. So what's the kinetic energy equivalent here? Same thing, K only. So we represented with the same thing. So the angular momentum is equals to root over 2ik. So the same thing we got here also. Yes or no? So just you can follow the analogy, guys. Okay. Done? This part clear. Chalo. Or else you can also write it here as, so if you need kinetic energy, K is equals to L square by 2I. You can follow this also. K is equals to L square by 2I. Done? Everything clear? Chalo. So let's move further. So let's take one simple question, the third question. What's the question says here? So two rotating bodies A and B of masses m and 2m with moments of inertia Ia and Ib. So where Ib is greater than Ia. So here there are two bodies. So here is a body A and here is a body B. And then, so whose masses are? The first one is m, the other one is 2m. So and their moments of inertia are, so the first one is Ia and the second one is Ib. And they clearly said here Ib is greater than Ia. Ib is greater than Ia. So find this part. Now, so have equal kinetic energies. So they both have the same kinetic energy. So now if LA and LB their angular moment of moment are respectively. So what's the relation between their moment of angular momentums? See, I know that. So they gave in terms of kinetic energy. So what's the moment of angular momentum in terms of the kinetic energy? So root over 2ik, right? So here 2 is the constant and they said both the bodies have the same kinetic energy. Both the bodies have same kinetic energy of rotation. So that means 2 is constant, K is same. So that means L is directly proportional to root I here. L is directly proportional to root I. Yes or no? So no. So if L is directly proportional to root I, here they said Ib is greater than Ia. As Ib is greater than Ia, so I can say that LB will be greater than LA, obviously. The angular momentum of the body B will be greater than that of the angular momentum of the body A. Simple question, right? Chalo. So let's go for the next concept, that is Newton's second law for the rotational motion. See, so first let's go for the Newton's second law in the linear motion, so then you can understand better. In the case of linear motion, we have studied the Newton's second law where, so the change in momentum dp is, the force is equals to dp by dt. The same thing we have studied this one, right? So then similarly, so I can write here for the, or else you can also write, so in place of this you can also write ma, so no problem, sorry, mv, fine. So in the case of angular, now in the case of angular terms, in the case of angular, so shall I write, so in place of F what do we get? The torque tau. The torque tau, so which is equals to D. So what is this P? What is this P? P is nothing but L, the P equivalent, L by dt. So the torque is equals to dl by dt, that's it. Or else if you want you can write that expression also. How? See here. So we know that L is equals to I omega. L is equals to I omega, right? So from here, so let's write the, let's do the differentiation. So what is this one? dl by dt on either side. So then d by dt of I omega, can I write? right? So chalo, so then I can write it as dl by dt is equals to, so I is a constant, moment of inertia of the body is a constant, so I into, so I can write d omega by dt, d omega by dt. So dl by dt is equals to, so I into, what is d omega by dt? Alpha, right? So I into alpha. So what is I alpha? We already studied in the last session. So that's nothing but torque. So dl by dt, so which is equals to, I alpha is nothing but torque. So if you want, you can derive, or else you can just go with the analogy. From here to here, you just do the analogy. Yes or no? Clear? Clear, guys? Everyone? Chalo. So fine. So now let's go further. So let's take one simple question here. So what's the question says? The angular momentum of a rotating body changes from a0 to 4a0 in 4 minutes. So a0 to 4a0. a0 to 4a0 in how many minutes? 4 minutes. So then they are asking what is the torque acting on the body. So the change in angular momentum is given, and then they are asking the torque. So we know that the torque is equals to dl by dt, dl by dt. So or else I can write here torque is equals to, so what is change in angular momentum? So final angular momentum minus initial angular momentum by, so what's the time, in what time it has changed? So let's say the time t. So now simply substitute the values. So the tau is equals to, so final angular momentum is 4a0 minus initial angular momentum is a0, right? So by the time taken 4 minutes, so which is nothing but 3a0 by 4. So 3a0 by 4. Hope they did not change any timing like minutes to seconds. So you can just keep that answer. So 3 by 4 a0. Option 1 is a correct one. Clear? Done? Everyone? Chalo. So next, let's move further. Let's move further. So now let's go for the conservation of angular momentum. Okay. So in previous case, linear terms, let's go for the first linear thing, then we'll do the angular. So here, let's write in terms of linear. So the conservation of linear momentum we already know. What is the conservation of linear momentum? Conservation of linear momentum so if F external, if the external force acting on the body is 0, if the external force acting on the body is 0, so then we know that the force F is equals to the dp by dt, right? So if the external force is 0, so then dp by dt will be 0. So which is nothing but the dp will be equals to 0. So what is dp? The change in momentum is equals to 0. The change in momentum is equals to 0. So if there is no external force acting on the body, so then the change in momentum is 0, which means the momentum will be constant. The momentum will be constant. So which is nothing but the initial momentum is equals to the final momentum. So this is a conservation of linear momentum. So now let's come to the angular part. Let's come to the angular part. So where, so we can say that the conservation of angular momentum. The conservation of angular momentum. See, simply you can do the analogy, guys, for whatever the derivations that we are doing in the rotational motion. You can simply do the analogy from linear motion to the rotational motion. Okay. So angular momentum. So what we can write here? So hope you guys understood now. So if there is no external torque, if the torque external is 0 on the body, so then we know that the torque is equals to the dl by dt, right? So if there is no external torque acting on the body, so tau is 0, which is dl by dt. So from here, so the dl is equals to 0. So the change in angular momentum is 0. So the change in angular momentum is 0. So which means, so the L is going to be constant. So which means, so the L is constant, right? So if L is constant means the initial angular momentum will be equals to the final angular momentum. So which is initial angular momentum is equals to the final angular momentum, right? Clear? So this is very, very important, guys. So if a body has initially the moment of inertia I1 and then its angular velocity omega 1, so its angular momentum will be I1 omega 1, L is equals to I omega, right? So I1 omega 1 is equals to, we can write, so I2 omega 2, I2 omega 2. Okay, clear? Done. So the famous examples so that they gave in the question or in the reference books. So two cases. So the first case, let's suppose a person is standing here and then he is holding some dumbbells or some weights in hands. So then now rotating with some angular velocity omega. So as person has stretched his hands, so the angular momentum will be more in this case. So as the angular momentum will be more, and then so the linear velocity the angular velocity will be less, moment of inertia will be more, I will be more. So why? He stretched his hands. So if I consider this my body as a origin, from origin the dumbbells are at a distance, from here to here r, from here to here r distance. So there are two moment of inertia, right? So moment of inertia is more, omega is less. So if the same person, if he fold his hands, previously he stretched like this, so now he folded his hands, okay? So then in that particular case, same person, how can he become fat from here to here? Same person. Okay, so let's suppose we gave him pizza, so then he ate and he became fat. So then, so now he folded his hands, okay? So legs same, okay, let's say. So then what happens here? The moment of inertia decreases. Here there is no external torque, right? So then if moment of inertia decreased, because previously so these dumbbells are at a distance r, now he folded his hands. So then what happens? So his angular velocity increases from here to here. The angular momentum should conserve because there is no external torque. So the torque external is equals to 0. So that means the angular momentum should be conserved. The angular momentum should be conserved. The angular momentum should be conserved. Done? Clear? Chalo. So this part is clear. So that's why here if it is the I1 omega 1, so here it is I2 omega 2. So they both should be equal. The momentum should be conserved. I can write I1 omega 1 is equals to I2 omega 2. So when he folded his hands, so he will be rotated with more angular speed. So you can also try that at your home. So take a wheelchair. So first take some dumbbells in your hand. So then you rotate. So then when you fold your hands, so then you can observe that your increased angular velocity. You can observe your increased angular velocity. You can rotate faster, okay, when you fold your hands. And when you stretch your hands again, so your speed will be decreased. The angular speed will be decreased because so there is no external force acting. So the momentum will be conserved. Which momentum? The angular momentum. So that's one example. So and another very famous example, so that is diver, not driver, it's a diver, swimmer. So like in Olympics we see, right? So in Olympics or some other games also we see, right? So where so the person stands at some height, so then pool will be there at the down, so then he jumps from there. So first he takes some torque, right? So first he takes some momentum, so then he jumps. So while he jumps, what he does? So he folds his body while he jump. So initially the person is here, so then he folds his body. So let me write. So here is a person. So here the person folds his body. So if he folds his body, so his angular velocity increases because there is no external torque here. There is no external torque. So then shall we say that the angular momentum should be conserved, the L should be conserved, the L should be conserved. So initially it's his moment of inertia is more, and then omega is less when he is at the top. So when he is jumping, so he folds his body. So when he folds his body, so what happens? His angular velocity increases so that he can make more number of flips in the air. Yes, understanding? So his angular velocity increases while diving, so that he can make more flips. Okay, so 1 flip, 2 flip, like that. So in the air he can make the more flips. So these are the very two famous examples of the angular momentum we can see. Okay, clear guys? Understood this part? Chalo. So next, chalo, let me have some water so you can just take this part. Yes, sorry. Chalo. So let's move further. This part is clear. So this is also clear. So let's move further. Let's go for the questions. So the question number 5. So what's the question says here? A round disk of moment of inertia I2 about its axis perpendicular to its plane. So a round disk they said. Okay. So its moment of inertia is I2. So about its axis perpendicular to its plane and passing through its center is placed over another disk of moment of inertia I1. So rotating with an angular velocity omega. So about the same axis. See here. So this is the first disk. So consider this is the first disk. About this the moment of inertia is I2. The disk 1, it has moment of inertia I2. So its angular speed is not there. Okay. So it is placed over another disk. This is placed over another disk which is rotating about the same axis, which is passing through the center and perpendicular to the disk, right? So whose moment of inertia is I1, and then so with an angular velocity omega. So it is rotating with angular velocity omega. So now this disk is placed about this one. This disk is placed on this, yes or no? So about an axis, a disk of moment of inertia I2 about its axis perpendicular to, so passes through its center. Okay, so this is placed on this. So when it is placed on this, obviously, so its angular speed will decrease, yes or no? So now those two, so the first one and the second one, so combinedly, so they move with some other angular momentum, so that is, so angular velocity omega dash. Okay, so what is its moment of inertia I1? What is its moment of inertia I2? So the first one, the second one moment of inertia I1, the first one moment of inertia I2, right? So from here to here there is no external torque. From here to here there is no external torque, right? So if there is no external torque, so I can say that, so the angular momentum should conserve. So the initial angular momentum should be equals to, so the final angular momentum. Yes. So what's the initial angular momentum? So this one has no angular speed initially. So I2 into 0 initially plus I1 into omega. This has angular velocity omega. So which is equals to, so now they both placed one over the another. So they both placed one over the another, so that their moment of inertia we can write I1 plus I2, because about the same axis. About the same axis. So I1, I2, so omega dash. So what we require? The final angular velocity of the combination. So I need the final angular velocity. So what we can write? Simply I can do here itself. So the I1 omega is equals to I1 plus I2 omega dash. I1 plus I2 omega dash. From here the omega dash is equals to I1 omega by I1 plus I2. I1 omega by I1 plus I2. So this is a new angular momentum. So not angular momentum, angular velocity. I2 omega, no. omega, no. I1 omega by I1 plus I2. Option 3 is the correct one. Clear guys? Done? Understood? Chal. So let's move further. So let's take one more question. So try to understand the question first. So what's the question says? A disk of moment of inertia I1 is rotating in a horizontal plane about an axis passing through the center and perpendicular to its plane with constant angular speed omega 1. See here. So there is a disk. So it is rotating about its axis which is passing through its center and perpendicular to the plane of the disk. It is rotating with some angular velocity omega 1. So its moment of inertia I1. So now another disk of moment of inertia I2 having 0 angular speed. So the second one, this is a disk 2. So whose moment of inertia is I2. So his this one's angular speed omega 2 is 0. So is placed coaxially on a rotating disk. So this one is placed coaxially. That means if it is the first disk which is rotating, so now the second disk which is at rest, it is placed on the first disk. So it is placed on the first disk now. So now both disks are rotating with constant angular speed omega 2. So let's take this one 0. So its angular speed 0. So now they both are rotating. So this is the first one and this is the second one which is placed one over the another. This is the second one. So they both are now rotating about the same axis which is passing through the center and perpendicular to the plane of the disk. So with some constant angular velocity omega 2. So what is the energy lost by the initial rotating disk? So what's the energy lost they are saying? See. So first we have to find what is its initial kinetic energy and what is the final kinetic energy of the combination. So then we can subtract. So the loss in energy will be initial minus final. Yes. So the first thing is just think generally. So the first one disk is rotating, the second disk is at rest, angular speed is 0. So now it is placed over this. So now the combination is rotating with some other angular velocity. Obviously from here to here the angular velocity decreases. Yes or no? From here to here, because you placed another mass on it, so that its speed, angular speed obviously decreases. Yes or no? Right? Chalo. So first let me go for the conservation of angular momentum. So let's write, let's do it in the next slide. As there is no external torque, acting on the body, you are placing another disk gently on this. Gently means very slowly like this. Okay now. So it is placed coaxially on a rotating disk. So you are not just placing like this, you are not throwing it. So if you are throwing it onto this, then there will be torque, there will be force. Yes or no? So you are not just placing it gently on it. Okay. So the torque, no torque, so that the angular momentum should conserve. Li is equals to Lf. So let's see what is initial angular momentum. So the initial angular momentum is equals to the final angular momentum. So what's the initial angular momentum? So I1. So the first one's moment of inertia is I1. So it's rotating with omega 1. It's rotating with omega 1. So which is equals to, so final. So second one, there is no speed. So that's why 0. So finally, so they both are placed coaxially and that axis is passing through the center of the both disk. So their moment of inertia will be added, I1 plus I2, and this is omega 2. This is omega 2. So from here I can write, so omega 2 will be equals to I1 omega 1 by I1 plus I2. I1 plus I2. So but what we actually needed, not the final angular velocity, we need the energy lost by the initial rotating disk. So what's the energy lost? So how do we find the energy lost? So let's find first the initial kinetic energy of the rotating disk. So the initial kinetic energy. So the disk 1 is rotating with half into moment of inertia I1. So it's rotating with how much? So omega 1. So omega 1 square. Yes or no? Half I omega square. So here half I1 omega square. The second disk is not rotating, its kinetic energy is 0 initially. So now let's see final kinetic energy. So final kinetic energy is half into, so half into, what's the moment of inertia of the final? The combination moment of inertia is I1 plus I2. The combination will have the moment of inertia I1 plus I2. So into, what's the angular velocity of the combination? this one. So which is I1 omega 1 by I1 plus I2 whole square. So that can I find the final kinetic energy here now? So the KEF, the final kinetic energy, is equals to, so what do we get? Half into, so I1 plus I2 into so here I1 square into omega 1 square by, in the denominator, so I1 plus I2 whole square. Okay, so square here, this part gets cancelled, so that we get half into I1 square omega 1 square by I1 plus I2. So this is the final kinetic energy. Now actually what we need, the loss in energy. So the loss in energy will be equals to, so the final kinetic energy minus the initial kinetic energy minus final kinetic energy. Initial minus final. Yes. So what's the initial kinetic energy we have got? Half I1 omega 1 square minus, so kinetic energy final we got half I1 square omega 1 square by I1 plus I2. So check the options. So we need in terms of I1 I2 omega 1, half omega 1 square we can take common. So what we can take common? Half omega 1 square. So what we can take common here? Half into, so let's take I1 also common, omega 1 square also common, right? So here it will be, the whole thing has come out, so I1 we can take common. So 1 minus, so 1 by 2 into, so 1 minus 1 by 2 into, so here I1 will be left, omega square you took it out, so here I1 plus I2, right? So take care of the calculation, guys. So here we get half into I1 omega 1 square into, so here it is 2 into I1 plus I2. Yes, in the denominator it should be 2 into I1 plus I2. So no calculation mistake, right? So this is the final. So we get, so this one gets cancelled, half into I1 plus I2, 1 cancel. So yes, fine. Yes. So now here, so it goes 2 into 2I1 plus 2I2. 2I1 plus 2I2. So here you can get minus I1. It goes one time, 1 into, so yes or no? So 1 into I1. Yes. So then I can write this as, in the next page I can write, so half I1 omega square, half I1 omega 1 square into, so in the numerator what do we have here? So 2I1, so minus I1, which is I1 plus 2I2, I1 plus 2I2 by, in the denominator, so 2 into I1 plus I2, so 2 into, here it is 2 is there, huh? I1 plus 2I2, so is equals to, so 2 into I1 plus I2, 2 into I1 plus I2. Right, so that's it. So square is not there. So check the options once. According to our we have got half I1 I2, I1 plus I2, omega 1 square is fine, half is fine. So just take care of the calculation. So where did we mess up with the calculation? See here. So let's do from the starting. So initially, so it has moment of inertia I1, so omega 1, so half I1 initial momentum, initial angular momentum is I1 omega 1 is equals to, final will be, so it's moving with omega 2, so I1 plus I2 omega 2, fine. So from here omega 2 will be I1 omega 1 by I1 plus I2, fine. So what's the initial kinetic energy? Half I1 omega 1 square, fine. So final kinetic energy will be half into I1 plus I2 into, so the final momentum angular velocity is this one, I1 omega 1 by I1 plus I2 whole square. Yes, fine. So here also, so then we have got half into, so here when we take half out, here I did the calculation mistake. When we take half out, there will be no 2 right here. If it is live, you guys would have told me, but I am recording, so I don't want to stop and record again. So just it's a human mistake. Okay, so I am also human, not a robot, right? Chal, see here. So what is initial kinetic energy minus final kinetic energy? So half I1 omega 1 square is the initial kinetic energy minus, so the final kinetic energy we got half into I1 square omega 1 square by I1 plus I2. Yes, fine now. So I can take half I1 into omega 1 square out. So here half you took it out, total thing you took it out. So 1 minus. So here the numerator part we left with I1, right? So by, so in the denominator we just have I1 plus I2. In the denominator we just have I1 plus I2. So here it will be half into I1 omega 1 square into, so here I1 plus I2 is a LCM, so that here we get I1 plus I2, so it goes I1 plus I2 times, so I1 plus I2, so minus I1, yes or no? So 1 time, so minus I1, so here this gets cancelled. So then we have got half into, so in the numerator we left with this I1, you write it inside I1 I2 by, so in the denominator I1 plus I2 into omega 1 square. Just rearrange the terms. Okay, half into this I1 also I am writing inside. So I1, already I2 is there, I1 into I2 by I1 plus I2 into omega 1 square. Yes, so half I1 I2 by I1 plus I2 omega 1 square. Option 4 is the correct one. So the procedure is easy, but the calculations you have to take care of. So these calculations you should take care, guys. Done? Clear? Chal. So let's move further. So what's the question says, the next one? So the next question, so the question number 7. There are two disks of same moment of inertia rotating about their regular axis passing through the center. Regular axis passing through the center and perpendicular to the plane of the disk with angular velocities omega 1 and omega 2. So they have the same moment of inertia, they said. So they have the, so this is the disk 1, so which is rotating about its axis, perpendicular axis, so which has angular speed, angular velocity omega 1. So there is another disk, so which is of same moment of inertia. Its moment of inertia is I, so its moment of inertia also will be I. So rotating with omega 2, so angular velocity omega 2. So now they are brought into contact, so contact face to face, coinciding the axis of the rotation. So if it is the axis of rotation, already one disk is rotating, so now you are placing one more disk face to face. So here the face of one disk, and you are placing another disk on it. Okay, so the expression for the loss of energy during this process, the same question, previous type question. See here, so those two are placed now coaxially like this, so their moment of inertia will become 2I. Initially I considered I, so now the moment of inertia will be 2I. So the new angular speed, let it be omega dash, right? So now see here, so there is no external torque, so I can say that, so the initial angular momentum will be equals to the final angular momentum, right? So what's the initial angular momentum? Let's do the calculation. So I omega 1 plus I omega 2. The first one angular momentum will be I omega 1, second one I omega 2 is equals to, so now the combination has, combination is nothing but I plus I into, so what else we left with? It's rotating with those two combined, so 2I, so I plus I into, so what's new angular velocity? Omega dash. So that I can take I common here, omega 1 plus omega 2 is equals to, so 2I omega dash. So from here I cancel, so I can write omega 1 plus omega 2 is equals to 2 omega dash. So the new angular velocity is omega 1 plus omega 2 by 2 is a new angular velocity. So now what they are asking actually in the question, so what is the expression for loss of energy during this process? So what will be the loss of energy? So the initial kinetic energy minus final kinetic energy. So what will be the initial kinetic energy, guys? So the initial kinetic energy, so the rod 1 is rotating, so half into, so the first disk moment of inertia I, and its angular speed, angular velocity omega 1 square, plus, so the second one is also rotating half I, the second one is rotating with omega 2 square. So therefore the initial kinetic energy of the combination is half into I, you can take common, so which is omega 1 square plus omega 2 square, right? This is the initial kinetic energy. The rotating disk will have which kind of energy? So the rotational kinetic energy. Other than that there is no energy, right? So then the final kinetic energy of the combination half into, so what's the moment of inertia of the combination? 2I into, so what's the angular speed? So what's the angular speed? So omega 1 plus omega 2 by 2 whole square. Omega 1 plus omega 2 by 2 whole square. Clear? Chalo. So now I can write half into 2I into, so here it is omega 1 plus omega 2 whole square by, so 2 square is 4. 2 square 4. Yes or no? Yes. So then 2 gets cancelled. I can write omega 1 square, omega 1 plus omega 2 whole square by 4 is a final kinetic energy. So now I need the loss in energy, so which is equals to, so the initial kinetic energy minus the final kinetic energy. Initial kinetic energy minus final kinetic energy. So what's the initial kinetic energy we got for the rotating disk? So for combinedly 2, half I omega 1 square plus omega 2 square. Yes or no? So into, so minus, sorry. So what is this one? So we have got here for the second one, so omega 1 final is omega 1 plus omega 2 whole square by 4 by 4. So you can write it like half into I, so omega 1 square plus omega 2 square, right? So into here it is, we can write it as, so you can if you want you can expand this one, omega 1 square plus omega 2 square plus 2 omega 1 omega 2, right? So by 4. So here the LCM will be, so what will be the LCM? This is omega 1 square, right? Yeah. So omega 1 square, yeah. So the LCM is, so 4 is the LCM, this goes 2 times. So 2I, it goes total 2 times. So 2I omega 1 square plus 2I omega 2 square, or else you can just write here I should be there, na? So sorry, my again calculation mistake. Omega 1 square plus omega 2 square into I should be there here. So nothing missed. So here I, write I. Okay, so let's do one thing here. So let's do one thing. So let me take half, or else let's take LCM, fine. So LCM 4, see it goes 2 times. So 2I omega 1 square plus 2I omega 2 square, just I am expanding it inside. So it goes 1 time. So minus, so I omega 1 square minus I omega 2 square, so plus, sorry, minus 2I omega 1 omega 2, so 2I omega 1 omega 2, so by 4. So then what we can write, so big expression we got, so 2I, so let me write that whole expression here, 2I omega 1 square plus 2I omega 2 square minus, so I omega 1 square minus I omega 2 square, so minus 2 times I omega 1 omega 2 by 4. So now I can write whole by 4. So I can write 2I omega 1 square I omega 1 square, which is I omega 1 square, plus here 2I omega 2 square minus I omega 2 square, which is I omega 2 square, so minus 2I omega 1 omega 2, so by 4. So just the calculation, guys. So I am taking common, so I can write omega 1 square plus omega 2 square minus 2 omega 1 omega 2, so by 4. So what is this one? I into, so I can write here omega 1 minus omega 2 whole square, I into omega 1 minus omega 2 whole square by 4. So I into omega 1 minus omega 2 whole square by 4. I into, so omega 1 minus omega 2 whole square by 4. Option 2 is the correct one. Clear a concept? So just take care of the calculations. So the calculations will be lengthy. That's it. Done? Clear everyone? Chalo. So next, this is done. So the next question, question number 8. What's the question says? A thin circular ring of mass m and radius r rotating in a horizontal plane about an axis vertical to its plane with a constant angular velocity omega. If two objects of mass m be attached gently onto the opposite ends of the diameter of the ring, so will then the ring will then rotate with a angular velocity of, see here question, a thin circular ring. First there is a ring, this is a circular ring, so which is of mass m and radius r rotating rotating in a horizontal plane about a axis vertical passing vertical to its plane with a constant angular velocity omega, with a constant angular velocity omega. If two objects of mass m be attached gently, so now, so for this circular ring, so there are two masses attached, so here one mass attached and at the end, so one more mass attached. So this circular ring will have radius r and from here the radius r. Yes or no? Chal. So opposite ends of the diameter of the ring. So the ring will now rotate with the angular speed of, so about this axis the ring will rotate with a new angular speed, new angular velocity omega dash. So the simple thing, there is no torque, you are placing them gently, so that means slowly. Okay, so there will be no external torque. So if there is no external torque, so we can say that the initial angular momentum is equals to, so the final angular momentum, both will be same, right? So what's the initial angular momentum we can take? So the Li is equals to, so Lf. So what's the initial angular momentum? So I into omega initially, so which is equals to, so the new angular momentum. So what's the new new angular momentum? Omega dash. So what's the new moment of inertia? What will be the new moment of inertia? Tell me. Already ring about its axis has mr square, right? Plus 2 mr square, shall I write? The new moment of inertia will be, initially this one has already got, the ring has already got mr square. So the ring will have the moment of inertia will have mr square, because they said circular ring and about an axis vertical to its plane with a constant angular velocity omega. So that's why it's mr square. So now these two masses are placed at r square, mr square plus mr square, these two, right? So that's why the total moment of inertia for this will be 2 mr square, 2 mr square. Yes, so now I can write, so the new moment of inertia, let it be I dash or I1 or I dash into, so the new angular velocity omega. So initially it is mr square into, so the omega, let it be, so I dash, so which is 2 mr square, so which is omega dash here, so which is omega dash, right? So their masses are small m mass, right? Sorry. For the small m mass means, so 2 mr square plus mr square, capital mr square, let me write this way, 2 mr square plus mr square into omega dash. Now you'll get the correct answer, see here. So then we can write it like, so mr square into omega is equals to, so what is this one? So we can write omega dash we required. Omega dash will be equals to mr square into omega by, so here 2m r square plus m r square. So here you can cancel out r square, r square. So the new angular velocity will be m omega by, so 2m plus capital M. 2m plus capital M. So m omega by, so 2 small m plus capital M. So m omega by, so 2m plus m. See, understood a concept? Initially first the ring is rotating. So now 2 more masses are attached. So now these 2 masses also will have the moment of inertia. Yes or no? So initial angular momentum will be I omega. So what is I? Only the ring is rotating. So mr square. So the ring mass is capital M. That's why m, and its radius is capital R. Okay, mr square. So now there are 2 small masses, small m are added. So the what will be the new moment of inertia? So this moment, its moment of inertia is small m into r square. Its moment of inertia will be small m into r square. That's why 2mr square plus. So the whole ring will have again the moment of inertia mr square. So that's why 2mr square plus mr square. So this is small m here, because these 2 masses are of small m mass. Here they clearly mentioned. Okay. So now omega dash is this one. Done guys? Clear? Everyone? Chalo. Hope you guys understood how to solve these questions now. So the conservation of linear momentum. So the 9th question, a thin circular ring of mass m and radius r is rotating about an axis with a constant angular velocity omega. 4 objects with mass small m are kept gently to the opposite ends of the perpendicular diameters of the ring. So the angular velocity of the ring will be, see, so initially this is the ring, so which is rotating about its axis. This is of radius, so it's rotating about its axis with angular velocity omega. So now 4 objects are placed on this ring on its diametrical ends. Here small m mass is placed, here small m mass is placed, here small m mass, and here small m mass. So if from here to here radius r, here to here radius r, here to here radius r, and here to here radius r. So initial angular momentum will be I into omega. So what will be the final angular momentum? So first final moment of inertia, which will be equals to whole ring first mr square plus, so there are 4 masses, so 4m into each radius is r square. So this is a new moment of inertia. Now it rotates about this axis with angular velocity omega dash. Now you can go for the, so the initial angular momentum is equals to final angular momentum. So what is that? Initial angular momentum is I, which is mr square into omega is equals to final moment of inertia mr square plus 4mr square, right? So into, so the new angular velocity omega dash, right? So from here, so what we need omega dash, right? So we need omega dash, so which is equals to, so mr square omega by mr square plus 4mr square. That's it. So we can cancel r square, r square, r square, right? So omega dash will be equals to m omega by m plus 4m, m omega by m plus 4m, m omega by m plus 4m. So this is the correct answer. Done? Clear? Sure. So a disk is rotating with an angular speed omega. If child sits on it, which of the following is conserved? If the disk is rotating, once the child sits, so what happens? Its angular velocity decreases, right? Its moment of inertia increases. So that angular momentum will be conserved. Same thing, when you place a disk, the constant disk on the rotating disk, what happens? So the angular velocity decreases, right? Moment of inertia increases. So we can say that the angular momentum will be conserved because there is no external torque on it. Done? Clear? So can you guys take this question as a homework 1? This question has a homework 1 and same previous question type, homework 2. So this question homework 3 and this one homework 4. If we are not getting, I'll solve them in the next class. Okay. So this is homework 5. Chalo. So that's it. Yes. So that's it from my end, guys. So this is all about the angular momentum. So in the next session, we'll start the rolling motion. Okay. So till then, keep studying. All the very best. Bye. Take care.